Hello, good morning, everyone. This is Jeff Dunham with BEA Sensors. Today's webinar will be BEA Inc. Technologies, how it works. Let's get started. Technology. It's difficult for one sensing technology to do it all. Things we must consider: cost, performance, power, installation benefits, and challenges. Challenges may be one of the biggest factors possibly. Combined technologies often provide better total solutions. To satisfy a diverse door market, BEA invests in 3 different sensor solutions or technologies and 3 local R&D and global teams. Some examples are microwave Doppler radar, best solution for motion. Optical or light is the best solution for presence. BEA has been providing activation sensors for 47 years and providing local USA support for 25 years. Here are 3 of our primary non-contact sensing technologies. Left to right, we have radar or microwave sensors, microwave frequency. Those are interchangeable terms in our industry, so radar and microwave are one and the same. In the middle, AIR or active infrared. And then on the right, LZR or laser. This would be the newest and technology, state-of-the-art technology. We'll describe all 3 of these here in this presentation. Methods of detection: the electromagnetic spectrum or force, the energy transmitted and then received by a sensor, whether it's microwave, Doppler, or infrared, types of infrared. And we'll describe in more detail both of those. And then we have mechanical forces where we have pressure or displacement or deflection. A sensor signals a given door system electrically and then senses people or objects or vehicles optically. We are in our infrared range here. One of the technologies, the first one we'll talk about, the motion component or the motion technology, whether it's called Doppler radar, microwave technology, microwave sensor, a motion sensor. Those are all interchangeable terms in our industry. Oftentimes, motion is misapplied or misunderstood or misstated, where motion should not be applied to other technologies that are detecting static or presence sensors. In this case, a motion sensor implies it's a microwave or Doppler radar sensor. Some of the different types, the first initial types of sensors utilize what's called a horn antenna. This is what's emitting the microwave frequency and internally has adjustable shutters to direct the detection field and shape it accordingly. That's discontinued as years ago. Today, we're using a flat planar antenna. These are 3 of the sensors. You may recognize one or more of them that utilizes a flat planar antenna to determine the shape of the detection field. Additionally, we're using another, it's called DRO type of planar antenna, which does a very similar sensor pattern shape configuration like the antenna does here. We'll describe these more in detail on the coming slides. Doppler radar, microwave basics. Inside of the sensors, we have a transmitter utilizing a gun diode at 24.175 gigahertz. That's the frequency that all BEA Doppler radar products operate at. And then a receiver receiving that frequency, Schottky diodes. We emit a frequency, a wave of frequency, kind of shown here with this icon, and then it's bounced back or received by, in this case, the object, or described up here, the object, the red object, is the person or object entering a detection field. The frequency is emitted. Here's the wave over here, but as we approach the sensor, the frequency shifts or compresses, causing detection. We have a certain bandwidth range that we work in, and it shifts and changes, and we use all types of different algorithms and software tweaks to determine if it's a person, if it's a vehicle. There are different methods to do that. And as an example, person detection sensor, the Eagle, for detecting people, an example of the frequency shift at a person moving at less than 5.6 miles an hour, 400 hertz is what that frequency would be. And then the Falcon is a sensor for an industrial sensor, typically used to detect, could be people, but vehicles is a popular selection for that sensor. We're moving at a little faster rate, therefore a little different frequency shifting. Frequency shifting is what's causing detection. Inside of the sensor, each sensor will have its own antenna. Here we have 3 different types of antennas. The detection field, that's one of the ways to shape the detection field, but also the tilt, the physical tilt angle of the sensor, the mounting height and sensitivity are all other ways to shape the detection field. If we were, and this is a horizontal plane, as if we're above the sensor zone looking down towards the ground, here are 3 possible shapes by one of these 3 antennas. Likewise, if we look at a vertical plane looking off to the side of the sensor, the detection field or the size of the zone, the shape is determined by one of these antennas being installed in the sensor. Some of the sensors have interchangeable antennas, some are fixed where you cannot change them. And then coupling with the antenna, the sensitivity is key. The higher the sensitivity, the bigger the shape of the detection field. Obviously, the smaller the number, the smaller the detection field. This is kind of an example of using a radio component where the sensor is emitting a radio wave to create this detection field for objects and people to approach. Doppler radar basics. So here we have 2 short video clips. They're both the same initially. So on the upper left of each video, you see a kind of a white grayish circular object. That is a Doppler radar sensor. That's a microwave sensor. It doesn't matter what kind, it's emitting Doppler radar. And here we're showing the radio component of the radar. And you'll see we're going to have the video on the left will play first. The person walks toward the sensor. The video on the right will play next. The person walks away. And let's see how the frequency shifts or changes to both actions there. We can see the person walking toward the sensor. The waves are compressed, smaller, shifting to a higher frequency because they're compressed, smaller waves. So let's look at the one on the right. Person will walk away. The waves are farther apart, shifting the frequency in the opposite direction. By knowing this, knowing the frequency shift less or more will determine direction. We can use the direction to our advantage for determining direction and using it in applications. And with that, we can use the microwave as a uni or singular or one type of direction or bidirectional. We have bidirectional mode where we can detect approach and departing targets as detected, or unidirectional mode where you can detect the approaching target. There's also options for approaching a departing target in lieu of approaching, but in both cases, you're only detecting targets in one direction. And then we can couple with that unidirectional mode a motion tracking component. Upon initial detection, the sensor automatically switches from unidirectional to bidirectional, providing additional detection capability. We're doing that using 2 Schottky diodes. Those are the receivers that will measure the phase difference between the two. Infrared, optical, safety. We have different types of infrared. We have passive infrared, active infrared, or AIR, not just IR. IR, infrared, is a common term, but we differentiate it and separate it because it's more specific here at BEA. And I'll explain some of this on the next slide or two. We have active infrared and LZR or laser. From infrared, we have passive, PIR. We'll get into that shortly. And then we have different types of active infrared. That could be an LED based, where we have a reflection based infrared, a triangulation based infrared, or our standard photo beam infrared, where we have an emitter and a receiver looking at each other. Or we have on the right, the laser or time of flight technology. Light basics. Light is changed 4 ways. First, by reflection. In this example, we have light transmitted onto a mirror, or a flat mirror, or a beveled mirror. But in this case, it's a flat mirror. We're reflecting that light to a different area. We do this with our laser sensors. Next, refraction, where the light, in this case, enters a liquid or water and refracts the light to a different position. What you're seeing is not really where the object is. Thirdly, diffraction, where we diffract the light using, in this example, we have infrared emitter emitting light through, in this case, we're calling it a Fresnel lens or a prism that refracts the light into defined focused areas that we use for presence detection. And then lastly, absorption, where we absorb infrared and use that in a way to determine detection or not. Infrared can be absorbed by certain types of material and subjects. Passive infrared, PIR. It detects the difference of temperature. The sensing element rejects most objects not the same temperature as a person. A person could fool the sensor because it can't tell the difference. So we never ever want to use passive infrared for any static or present sensing ability. It can never be used for a safety sensor for an application. These type of sensors are very inexpensive to manufacture, and they're used primarily for access control and security as well. Security systems often use PIR sensors to detect movement in a room. It's looking for a motion component with a heat signature. If you don't have that, then it won't be detected. Active infrared reflection, or AIR, where light is transmitted from the sensor and reflected light is received back at a reduced value. And we'll show you more detail on the next coming slides. A reference value is stored and then compared to the current value. If there's a difference, the object detection or something has changed, detection would occur then. And there's types of reflection sensors. We have diffuse would be one type. This is typically creates a large flooded optical zone that can be difficult to control. This type of sensor is best used for stationary static environments, and the sensor must be in a fixed location. We also have a focused type that creates a small detection zone in a defined area. And you can typically have multiple spots with an improved signal to noise ratio, SNR. Also, it'll compare the values between the spots and the absolute value of all the spots. Using that with software algorithms will allow the ability to cause detection. Reflectivity, here's an example of a pedestrian door, and this example of this sensor is a dual technology utilizing Doppler radar, shown by the blue area would be motion detection, and then the reddish area would be the active infrared for presence detection or safety, using that component of reflectivity. Speaking of reflectivity with active infrared AIR, BEA's active infrared sensors send an output signal after the reflectivity of the emitted IR exceeds the upper threshold or falls below the lower threshold. With software immunity, the sensor's threshold limits will automatically adjust, we call tracking, to subtle changes in reflectivity. So this example is showing a baseline of an upper threshold and a lower threshold of infrared that we've emitting the infrared as we're showing in this image here on the ground and reflecting it back to the sensor. Anything inside the baseline is nothing. We don't show detection. Small changes, blowing leaves in here on the ground is not going to cause a change of reflectivity. But if a person enters or an object enters that enough to cause the upper threshold to exceed or the lower to exceed, but in this example, the upper threshold exceeds. And if it's there long enough, it will track and adjust that to a new baseline. The lower level is shifted, the upper level is shifted up to our new baseline. And that is adjustable during the installation by the installer as a timing component. You can adjust the amount of time or how long it takes to track and adjust that. Active infrared triangulation. This is really a distance measuring part where this type of product can be installed on moving objects on doors to cause detection because it's not dependent on reflection off the floor. It's simply a distance component. In this example, we're using a little bit of trigonometry, but create the distance, we have a position sensing diode in the sensor that determines the distance. If a person or object enters the field, it changes the angle and the location of the position sensing diode is shifted over here because the angle changed and a person entered the zone, thus causing detection. That distance is adjustable within the sensor and is great for on moving doors. Likewise, it could be installed in a fixed location as well, but typically a smaller detection field. Dual technology, microwave and optical, shown left to right. We have pedestrian and industrial applications where we're using Doppler radar to activate or detect movement, motion, and then infrared, active infrared, to detect static, slow moving, or stationary objects or people. Next, we get into laser, LZR, oftentimes referred to as time of flight or TOF. We'll explain the time of flight probably on the next slide. Here's a basic example of the components externally, what the sensor, and we have the laser transmitter or emitter, and then we have the receiver, and we have visible LEDs for detection and for the installer and users to see. Laser time of flight and basic principle of how it works. So inside the sensor, there's a laser diode and a photodiode. We emit the laser, it bounces off of an object or a target, and it's received with the photodiode. Since we know the speed of light, we simply divide by 2 how much time it takes to emit and receive. Using this formula, divide by 2 gives us a distance component, which is great because we don't need to use the ground or the floor or anything to be reflective. If, for example, if we rotate this whole thing 90 degrees and wanted to measure the distance to the floor, we could. But then once it determines that distance, we apply some math and pull up or reduce the distance, pull it up off the ground to the floor. So anything on the ground would never cause detection unless you wanted it to. Laser, time of flight, and scanning. The mirror will turn 1 revolution 66 milliseconds. In this case, this is a mirror inside of the sensor. The top part is where the laser diode is emitted. The bottom is a bigger area for the receiver photodiode of the sensor. The sensor rotates 1 rotation, 66 milliseconds, creating a large dynamic detection field. at the end result, in this example, over 16,000 pulses a second. Very fast because we're working with the speed of light. Laser time of flight and multiple curtains. This example of this sensor, we have the mirror we showed in the previous slide. We have the emitter and the receiver. What happens is it emits and receives 4 different curtains because the mirror has a 4-sided cube. Each side has a different bevel, 0, 2, 4, or 6 degrees. What happens is it disperses the field to a wider, or in this example on the right, a thicker or taller curtain. At 13 feet, the distance or space between the 4 curtains would be about 16 inches. You could just as easily, in this example, the sensor is mounted here at the floor, you could take the same sensor and mount it up on the wall and do the same thing vertically. You would have a little thickness of that curtain based on the mounting height, and then you could choose to use 1, 2, 3, or 4 of these curtains to detect whatever the application you could use it at. More information here, just describing the time component. We're emitting laser diode to a photodiode, divide by 2, how long it takes, gives you a distance of the object. I think we have an automation on the next slide. This will show a distance here. We're using 2 meters, a little over 6 feet. The time it takes to emit and receive, really hard to explain that time, 13 nanoseconds. That equates to, you can see, over 76 million pulses a second. That's incredibly high resolution. Explains why the laser sensors can detect very precise areas very quickly as well. And that's it, folks. Availability, pricing, warranty, tech service, you can call the main number at 800-523-2462. A couple of different email aliases there you can use to contact customer service or BEA tech support if you've got technical information for installation, wiring, even application suggestions. Those guys can help you with that. They can't help you with pricing, warranty, and ordering. That would be sales. And if speaking of sales, if I don't know where anyone is located on this webinar, but here is the sales inside and outside reps for your state or province.